All right, welcome to Unit 5, Reasoning. This is the start of geometry for us in this class. We're going to be talking about conjectures and conditionals today. Before we do that, just really quick, we're going to be talking about the difference between inductive reasoning and deductive reasoning. With inductive reasoning, that uses a number of specific examples to arrive at a conclusion. You can see inductive reasoning in this world by if you're training a dog, for instance, you're going to discipline that dog and you're going to give that dog rewards in order to get the dog to do what you want it to do. So like the dog realizes by specific examples on what appropriate behavior is. Okay, I went and dug in the trash and I get whooped every time, so I shouldn't go dig in the trash. That's its conclusion from specific examples. Perhaps every time it goes to the restroom outside, it gets a treat. So it's using specific examples to say, all right, now I need to associate using the restroom outside. So animals use this a lot. Also humans use this, obviously. Deductive reasoning, on the other hand, is something that wouldn't really work too well for trying to train an animal. Deductive reasoning uses facts, rules, definitions, or properties to reach logical conclusions from given statements. We follow the law because we're told to. All right, so deductive reasoning would be an example of that it's situations where we're told what's right or wrong, not that we learn what's right or wrong through experience, even though that can happen. So deductive reasoning is you're given a set of rules and you follow those rules. And like I said, training an animal, that doesn't really make sense to them. So they have to use inductive reasoning. But something like a computer has to use deductive reasoning. It stays within the constraints of the programming. So computers use deductive reasoning for the most part. They're starting to make, obviously, software that can do more of this inductive reasoning bit. Now, conjecture. That's a conditional statement reached using inductive reasoning. And we're going to see conjectures here in a minute. Conjectures are examples of conditional statements, and we'll get more into those. So I'm going to square a few numbers here and see if I can make a conjecture. So this is a number of specific examples. I'm going to be using inductive reasoning. And I'm going to compare the square to the original number. So 5 squared is 25. When I square 7, I get 49. When I square 4, I get 16. And when I square negative 3, I get 9. Remember, you're squaring the negative as well. So what is a conjecture that can be made for these scenarios? Just comparing the square to the original value, every single time it was greater than the original value. Even when it was negative, when I squared the negative, it became positive, so the 9 is greater than negative 3. So that will be my conjecture. If a number is squared, then its value is greater than the number. Then the square is greater than the number. A little bit of writing in today's lesson and throughout geometry. Okay, what is the truth value of the conjecture? Now, this is a conjecture, and for a conjecture to be true, it has to always, always, always be true. If there's ever one single time that it's false, then the entire conjecture is false. We saw cases where it was true up here, but is there ever a time that you could square a number and get a number that's less than or equal to the original number? There are many times. So this is actually false, but when I say that it's false, I have to provide what's called a counterexample. We assume that a statement is true until we prove otherwise. So here's my counterexample. 1 squared is equal to 1. Or perhaps I could have even used that 1/2 squared is equal to 1/4, where 1/4 is less than 1/2. So those would be my counterexamples. I actually provided 2. I only need to provide 1 counterexample in order to prove the statement to be false. This is really essential for the framework that we're getting set up for in geometry, where we're going to be doing a lot of proofs and stuff. And all your properties, that you've used in algebra, all your theorems, they are all written as conditionals. If you go back and look at them, they could be written in if-then form. So kind of leading into that now, a conditional statement is a statement that can be written in if-then form. We don't have to write a conditional statement in if-then form like I just did. I could have simply said the square of a number is greater than the number on that original one. That would still be false, but that's still a conditional statement. All right, here we go with example 2. Identify the hypothesis and conclusion of the following statements. The hypothesis is always the part that has to be met in order for the conclusion to be true. If a polygon has 6 sides, then it is a hexagon. That's a true statement, by the way. There's no way around it. Now, here's the hypothesis. And I'm going to use a P to represent hypothesis. That's usually pretty common. So P equals hypothesis. And Q represents conclusion. So if you ever see me using that notation, you'll know what I'm talking about. So the hypothesis is a polygon has 6 sides. Now you'll notice how I'm making that a complete sentence in and of itself. A polygon has 6 sides. There's a noun, verb, direct object. All right, now going into my conclusion, it is a hexagon. Now, I can't use the word it because that would be using a pronoun before you've described it, so let's make a complete sentence. A polygon is a hexagon. That way we actually have 2 statements that really stand on their own, 2 complete sentences here. One is the hypothesis, one is the conclusion. If this hypothesis is met, then the conclusion has to apply for the statement to be true. Now, if the hypothesis is not met with an object, like let's say a square, then this conclusion doesn't necessarily apply to it. Obviously, a square is not a hexagon. Let's move on to another one. Tamika will advance to the next level of play if she completes the maze in her video game. This doesn't look like it's written in if-then form. It's been switched around a little bit. The hypothesis actually is Tamika completes the maze in her computer game. Again, using a complete sentence, I did not say she completes the maze in her computer game, but this is the part of the statement that has to be met first. Now the conclusion happens. Now that she's completed the maze in her computer game, now this applies that she will advance to the next level of play. Tamika will advance to the next level of play. And there's my conclusion representing that, following the cue right here. Tamika will advance to the next level of play, period. All right, moving right along, here's a statement that's not in if-then form. So it says identify the hypothesis and conclusion of the following statement, then write the statement in if-then form. All right, there's actually 2 things going on here. It's not just simply any distance. It says a measured distance. So my hypothesis would actually be a distance is measured here. And my conclusion would be that that distance is positive. A distance is positive. First, it has to be measured in order for it to be actually positive. So now I'm ready to write it in if-then form. If a distance is measured, and here I can use the pronoun, then it is positive. Because that's in the same sentence, I'm referring to the distance that's been measured. All right, that finishes up this problem. All right, on this problem, on these problems, we're just going to determine the truth value. If true, explain your reasoning. I'll just kind of say that. If false, give a counterexample. We assume things to be true if we can't prove them false. Starting with the first one here, if you subtract a whole number from another whole number, the result is also a whole number. This one actually ends up being false. Whole numbers are 0, 1, 2, 3, 4, and so on, but does not include negatives. So actually I could do 7 take away 9, and that's negative 2. Negative 2 is not a whole number. It is an integer, but it's not a whole number. So this is false, and there's my counterexample. You have to provide a counterexample if it's false. Basically, if it had said if you subtract a whole number from another whole number, the result is an integer, that would have been true. That would have been fine. But as it is, no. Exact same instructions on part B. If last month was February, then this month is March. Please don't try to overthink things. This is true. March follows February would be my explanation. You don't have to usually, I'm not going to require you on a quiz or a test to actually provide your reasoning, because we assume statements to be true if you can't prove them false. In no way, no how could I ever find a time where the last month was February and the month is anything but March. Okay? That's impossible. Now, part C is the tail kicker. Okay? So y'all have probably gotten a pretty decent feel for this. Let's go ahead and take a look at this last one. When a rectangle has an obtuse angle, it is a parallelogram. Now, some people will cue into this obtuse angle and say, wait a minute, a rectangle cannot have an obtuse angle. So they're wanting to say that this statement is false. This statement is actually true, and it's kind of weird what happens here, and here's the reason why it is. I know you might be trying to throw something at the monitor and say, you're a moron, Mr. Bumgarner, but here's what the logic is. This is my hypothesis. A rectangle has an obtuse angle. Now, I cannot find a rectangle with an obtuse angle that would meet this hypothesis. Since I can never find that, I can't tell if this statement is true or false. I can't create a counterexample. Remember, the counterexample meets the hypothesis, but fails to meet the conclusion. Well, in this particular problem, I can't find a rectangle with an obtuse angle. I can't find something that meets the hypothesis. So the conclusion is inconsequential. It just doesn't matter. So this is a true statement since we can't prove it to be false. Since we can't provide an example where a rectangle has an obtuse angle but is not a parallelogram. Well, I can't find one of these to begin with. All right, they only have right angles. It's by default true. So whenever you have a statement where the hypothesis is in itself false, you have a true statement, actually. I know that's kind of weird, but that's how it works. Converse really quick. This is moving right along to our last example. The converse of a statement is formed by exchanging the hypothesis and conclusion of the conditional. So I'm going to take a look at a couple of those, if not just one, I believe. Yeah, actually. If two angles are complementary, then the sum of their measures is 90 degrees. The truth value of that statement is actually true. That's what it means for angles to be complementary. They add to 90. I cannot find a pair of complementary angles that don't add to 90 degrees. Now, write the converse of this statement. So that's where we're going to swap the hypothesis and conclusion. So now, if two angles, let's see here, the conclusion was the sum was 90 degrees. That's now going to be my hypothesis. If two angles measures have a sum of 90 degrees, then now my hypothesis becomes my conclusion. They are complementary. That one is actually true as well. All right, so here's something special that happens. When the statement is true And the converse is true as well, as is the case here. If two angles measures have a sum of 90 degrees, then they are complementary. That means what we have here is a definition. This is exactly what it means for angles to be complementary. And this is exactly what it means when angles have measures that add to 90 degrees. So they are complementary. So this is a definition. What we call this is a biconditional. The conjunction of the two statements is a biconditional. This represents a good definition since both parts of the statement have to imply the other. Here, if angles add to 90, they are complementary. If they're complementary, they add to 90. That's what this means. And here's how the biconditional would look. Two angles are complementary. See, I start with the hypothesis, which really it doesn't matter which one you start with. I could have used the converse one. If and only if the sum of their measures is 90 degrees. And there's my biconditional, is that one perfectly implies the other. Now, can you always do this for any true conditional statement? No. Only conditional statements where their converse is also true can you do this. Sometimes the converse is not true of a true statement, so you can't make a biconditional out of it. It means it's not a good definition. All right, that concludes our first day of geometry. That's reasoning. I expect there to be questions. You let me know what you got.